couple things. What I'd like to start with, if you were able to watch the video yesterday, I do want you or need you to sign up for AP Classroom. Okay. So if you have not signed up for AP Classroom, please make sure that you do that sometime in the next 24 hours. Tomorrow, I'll have a little assignment for you to do on AP Classroom. It'll probably take you like 10 to 15 minutes, so don't freak out too much. And eventually here, I would like to start using Fridays sort of for a lab day. I know I kind of, in that first day I'd mentioned, I'm not quite sure how I'm going to handle labs, but AP just sent out an email to all the AP Chem teachers across the country and said, hey, you need to be doing labs. So spoiler alert, I'll be doing some sort of lab format with you on a Friday. Most likely it'll be me recording myself, playing with chemicals, and then you get to kind of analyze what I'm up to, and I'll give you some data and things like that. So it's going to be tough, and I don't quite know how well it's going to work, but again, we'll try our best. If you were here in person, we'd have 2-hour labs on Fridays. So I don't know if what we got going on now is better or worse. Hold on. There we go. But anyway, so that's just kind of the tentative plan. So if you haven't signed up for AP Classroom, please do so. It's in the plans from yesterday, and it's also in the plans today. There's a link there. You can just click right on it. It'll take you right to the website. When you sign up, and I did say this yesterday too, please make sure that you use a personal email address and not your school email address. That sounds weird because obviously this is for school, but the whole idea there is that if you're a senior or even if you're a junior, these test scores, when they come out in July. So if you're a senior and you graduate, you won't see your test scores if it's tied or linked to your school email address, because that gets shut down after you graduate. So in order to access your scores in the summer after the class is all done, it's probably best to just sign up for AP Classroom using a personal email address instead. Because even if you're a junior, there's probably a decent chance that you're taking another AP class next year. And it'll be the same account to access that website next year too. And all the AP teachers are using the site now because it's kind of a direct source of all sorts of AP content. So it's a really good resource for us. So, all right, long story short, please sign up if you haven't signed up. And if you need help with that, you can certainly shoot me an email or pop into my office hours and I'll help you out. But there's a link, there's the join code on It's Learning. So hopefully you can figure that out and get on there, and we'll use that tomorrow, okay? For today, if you have your unit pack, we're gonna run through 1.3 today, so you can grab that out. With this unit pack, by the way, if we were actually here, I wouldn't give you this big giant stack of paper stapled together. I would just slowly but surely kind of trickle it out, and you would get 1 a day or 2 a day or whatever, depending upon where we're at. So if you want to take the staple out and just use a 3-ring binder, please do so. I think it's probably a much easier, nicer way to handle this. And again, I'll 3-hole punch everything I give you. So eventually when we have another supply drop or at the high school, you'll pick up new stuff from me, and I'll have that all 3-hole punch too. So really a 3-ring binder is probably your best bet for this class. But anyway, so grab 1.3, we'll go through it. It is 100% review. So the things in 1.3 are the things that you have talked about last year. Again, it's been a little bit, so hang with me. But I hope it makes sense, and I'll try to keep a decent pace. If I'm going too fast, please feel free to slow me down either through chat or through unmuting yourself and asking a question or whatever the case may be. But I'll go into present mode now, and we'll hop in and we'll get started. All right, so today it is all about the elemental composition of pure substances. So again, every single day I've got these objectives. These are tied right to AP and their resource or their big giant curriculum for this class. And the goal for today is to explain the quantitative relationship between the elemental composition by mass and the empirical formula of a pure substance. So a couple of those things you've obviously seen before: empirical formula, molecular formula. These are the things that you talked about last year. And that's really what today is going to be all about. So a couple definitions to write down, and a couple problems to try, and then we'll call it a day. It is a review day, more or less, from some stuff from last year. So first definition, pure substance. A pure substance is, hold on, I got to unfreeze my board. There we go. A substance that contains only one element or, oops, not of, or or compound, okay? So something that is nothing but one element, or something that is nothing but one compound and nothing else there, right? That's what we would call a pure substance. Okay, so I'll give you a chance to write that down if you haven't written that down. It's not the most profound definition you've ever written down, but so right underneath that then, and I'll go to the next slide in just a second, but right underneath that you see two examples, right? You have pure substances can be elements, or pure substances can be compounds. So the example I have for elements are diamonds. Okay, so diamonds are pure carbon, nothing else. It is 100% carbon atoms arranged in a way, and arranged in a very specific pattern, and that's diamonds. Okay, it's a pure substance, nothing but carbon. Compounds are molecules, right, or more than one atom stuck together. So you can have a pure substance that is a compound. Water is a great example of this, right? Water we know is H2O, so it's little molecules with one oxygen and two hydrogens bonded together, and you can have pure water. Now, more often than not, when you're talking about drinking water or water in a pool or in the ocean or wherever, there's usually a whole bunch of stuff dissolved in it, right? So it's never really pure, but in theory, we could obviously purify it. There's plenty of methods used to kind of get a lot of the dissolved substances out of water, and you can have a pure sample of water, and it contains nothing but H2Os and nothing else is present. That would be a pure substance as well. So again, pure substances, basically it's one thing, either pure element of one type or pure compound of one type, but nothing else is there, okay? And I think you probably would have known that, or certainly could have deduced that without me writing that definition down. But all right, so now this is going to lead us into empirical and molecular formulas. This is stuff that you learned last year, and a lot of this is actually pulled from last year. So there are some wording or some little paragraphs that are going to look extremely similar to last year's note sheet, if that rings a bell. Yeah, I took it right from it. This is more or less a review again. So hang with me. So formulas like NO2 show that there are twice as many oxygen atoms as nitrogen atoms, okay? So we have little subscripts, right? That little 2 next to the oxygen is representing the fact that we have 2 oxygens for every 1 nitrogen, right? So the ratio is 2 to 1. In a mole of water, you could also say that there are 2 moles of hydrogen and 1 mole of oxygen, right? So you can also use those ratios or those subscripts not only as atoms, counting atoms, right, 2 to 1, you can also use it as moles, 2 to 1. So the last thing I have here is that this always has to be true, right? You cannot have water, or what we call water, unless you have this exact ratio of hydrogen to oxygen. If you switch it at all, right, if you add an extra hydrogen, it's not water anymore. If you add an extra oxygen, it's not water anymore. It must be H2O. If you mess with that, you've got some other substance, right? The prime example of that is like hydrogen peroxide. Hydrogen peroxide is H2O2, okay? You can drink water, and we need it, but hydrogen peroxide in high concentrations will essentially eat away at your skin, all right? Now don't freak out, because obviously it's a first aid, it's in first aid kits and stuff, right? You clean cuts with hydrogen peroxide, but that's like 3%, okay? Really, really low percentage stuff. If you get the high percentage stuff, that stuff will absolutely destroy tissue. It's not good. And I've actually messed with and played with some 30% stuff, and I got it on my hand without realizing it, and I had like all the skin on my fingers had died for like a week, and I had like white fingers as the skin was dying. Yeah, it was really, really fun stuff. Anyway, I used to work as a real chemist, by the way, if you didn't know that. So that was when I was an actual chemist. We had some high concentration hydrogen peroxide. But anyway, so subscripts, these are atom ratios. If I have 1 molecule of MgCl2, that means I have 1 atom of magnesium, 2 atoms of chlorine. Again, these subscripts are just going to show us ratios. If we use moles, again, please don't ever forget, a mole is just a really big number. So if I have 6.022 times 10 to the 23rd molecules of magnesium chloride, that means that I have 6.022 times 10 to the 23rd atoms of magnesium, and double that, which is 1.2 whatever, times 10 to the 24th atoms of chlorine, right? So you can use this as atom ratios, you can use it as mole ratios, but don't ever forget that a mole is just a number. It's just a really, really, really big number, and we can use these ratios for that as well. So in this formula, N blank O blank, you can fill in a whole bunch of different numbers, and this is where a problem kind of arises. You can have way more than one compound that contains the same two elements, okay? For example, all of these formulas listed below do exist. Nitrogen and oxygen can combine in a whole bunch of different ratios. So the problem is when we want to identify what we have, just saying that nitrogen is there and oxygen is there isn't going to tell us the whole story. So let me kind of tie this back into yesterday's lesson. Yesterday we talked about mass spectrometry or mass spectroscopy. I talked about that second word in my video just a little bit. Please don't lose sleep over spectrometry or spectroscopy. When you hear that word, all I really want you to think of is it's some sort of instrument or machine that helps chemists analyze chemical samples, okay? So a mass spectrometer is an instrument that gives you ratios of different elements in a chemical sample. So that's all well and good, but if I put a sample in that instrument and it says, hey, you got some nitrogen and you got some oxygen. Okay, that's great, but I have no clue what I have because there's a lot of different options for what that could be, okay? So we have to go a little bit further, and this is where we talk about molecular formulas, empirical formulas, and we start looking at percentages and working on some of the math of this stuff. But let's keep going. So an empirical formula. You did learn this last year. An empirical formula is the simplest whole number ratio of atoms in a compound. Okay? If you have the simplest whole number ratio of atoms in a compound, we call that an empirical formula. All right, so again, I'll let you write that down. The next definition, which is on the next slide, is a molecular formula. A molecular formula is the actual formula, meaning the real formula for whatever substance you're looking at. It's not reduced, it's not simplified like the empirical formula. It is the actual formula of whatever you got. All right, so again, let me use the example of hydrogen peroxide. Hydrogen peroxide, the molecular formula is H2O2, but I can reduce that, right? I could have HO, which is the empirical formula for hydrogen peroxide. So that's the difference. The molecular formula, which I'll go to right now, is the actual formula, and that's all I'm gonna write. Okay, I have a bunch of lines here, but that's all I really need. It's the real formula, the actual formula of whatever substance you're looking at. Okay, and sometimes the actual formula or the molecular formula, it is the empirical formula, right? Water, H2O. Can I reduce that any further? No, I can't. So in that case, the molecular formula and the empirical formula are the same thing. But oftentimes, especially as you get further and further in chemistry and you look at bigger and bigger molecules, most often you can actually reduce those formulas down further to get an empirical formula, okay? So because certain molecules can have the exact same empirical formula, it can really make identifying compounds difficult, okay? So for example, there are more than one molecule that exists that have this ratio of nitrogen to oxygen. So if I took a sample and I plugged it into my mass spec, and that instrument does its magic and it does its stuff and it spits out a readout to me that says 46.6% nitrogen, 53.3% oxygen, I don't really have the whole story. I don't know precisely what that stuff is. I would need more information, right? Because there's more than one compound that has those ratios. So the mass spec can get us these percentages, which is really nice and useful, but it doesn't tell us the whole story always if the readout or if the sample is giving us percentages that can be applied to more than one type of molecule, okay? And by the way, if I'm going too quick or if there's questions, I see the chat is blown up. I don't know if that's all just a bunch of hears. I'm assuming that's a bunch of here's. Yeah, it's a bunch of here's. By the way, if you haven't put here in the chat, please do so I can mark you present for today's class. But if you do have a question, please feel free to unmute. Please slow me down, punch it in the chat. I'll try to keep an eye on it and make sure that if there's an actual question in the chat that I catch it, or if somebody else catches it, just unmute and yell at me and I'll stop. But anyway, okay, so here are 3 formulas. These are molecular formulas. Please reduce them to the empirical formula. Go for it. I'll give you like a 20-second head start. I think this is rather simple. And again, you did do this kind of stuff last year. Okay, for the first one, I can obviously reduce that. I've got C6H12O6. I could divide all 3 of those values by 6 and reduce this to the simplest whole number ratio, again, which is called an empirical formula. And I get CH2O. You can, if you want, write subscripts of 1, but it's kind of redundant, right? It's just not necessary, because when you write an element in a formula with no number behind it, it's implied that there's only one of those, right? So if you wrote C1H2O1, it's not wrong, it's just not necessary either, right? CH2O would be the appropriate way of writing it. For the next one, we can reduce this as well. We can divide all of those by 2, and we end up with a formula of C4, H5, N2O. Okay, and last but not least, if I were to do this one, I get C4, H7, Br2. Okay, really, really simple. If you have a molecular formula and you want to turn it into an empirical formula, you just reduce it until they are the smallest possible whole numbers within that set of values. Okay. All right, let's try number 1, and I'll kind of do this one for you. And I'll explain some of this stuff. And again, it really is stuff from last year, so it should feel sort of familiar. But I'll do this one for you, and then I'll kind of give you a chance to try the next couple on your own. So what is the empirical formula of a compound that contains 18 grams of carbon and 4.03 grams of hydrogen? First things first, we want to start with what we're given. So we're given grams. I have this many grams of carbon. I have 4.03 grams of hydrogen. And I'm now going to convert both of these to moles, okay? When we're talking about formulas, empirical or molecular formulas, we need to compare the mole ratio between the substances in order to get these appropriate formulas. So I'm going to take my 18 grams and I am going to convert it to moles. So I use the molar mass of carbon off my periodic table, and I set it up like that. I'll punch it in just a second. For the next one, I convert my grams of hydrogen into moles of hydrogen. Okay, same thing. I use its molar mass off the periodic table. Again, it's only day 3 of AP Chem, so please be careful. Your hydrogen is no longer 1, right? On your new periodic table, it's 1.008. Okay, so please don't forget that. And again, feel free to complain all you'd like, but it is what it is. So sorry. Anyway, so 18 divided by 12.01, I think with sig figs is just 1.50 if I'm not mistaken. All right, and then 4.03 divided by 1.008. I'm getting 3.998, which again, if I chop it off for 3 sig figs, I get 4.00 moles of hydrogen. Okay. And once you get the moles, we need to use these ratios to give us a whole number formula, right? So now I kind of take this math and I set up a fake formula. You could kind of think of it as, I have C 1.50, H 4.0. and I divide both of those mole values by the smallest of those numbers. So I'm going to divide those by 1.50. And when I do that, I should hopefully get whole numbers, but not always. But if I take that and I divide by 1.5, I now get carbon 1, right? Because 1.5 divided by 1.5 is obviously 1. And then if I take 4 divided by 1.5, I get 2.666 repeating. Okay, so I have H 2.667, and that's a repeating decimal. These aren't whole numbers. We can't stop. We have to keep going. We have to make sure that our empirical formula has whole numbers. So this is the point where we need to either, or where we need to multiply by some value so that both of these subscripts are whole numbers, right? So the decimal of these values is how we're going to determine what to multiply by. So 0.667 or 666 repeating is 2/3. So if I were to multiply this formula by a factor of 3, I am going to get whole numbers for both of those subscripts, which is what we're looking for. Okay, I multiply by 3 and I get a new formula of, don't mind me, I'm just falling. C3H8, okay? So if you look at this, this is our empirical formula. Can you reduce those values any further? You can't, right? 8's not divisible by 3, so we can't reduce those anymore. This is our final answer. So that was the steps, okay? I hope it kind of rings a bell from what you did last year, right? There was a little bit difference. If you look at problem number 3, or when we get to problem 3 in just a little bit here, we'll do the full problem that you guys ended up doing last year. But yeah, that's kind of the general steps. If you're given mass, you switch to moles. Take those moles, divide by the smallest value that you solve for, and then figure out or determine whether you have whole number ratio. If you don't have a whole number ratio, you need to multiply by some factor in order to turn them into whole numbers. If when it's all said and done, okay, let's say you finish a problem like this and your final formula can still be divided, right? Something's gone wrong. Either you've multiplied by the wrong number at the end, and then maybe you can just cut it in half or whatever you need to do to make it whole numbers. Or you've just screwed something up along the way, right? So you got to kind of double check your work, because when you're all said and done, you absolutely should have a formula that can't be divided any further. So go ahead and try number 2. This one skips the grams step. All right, the grams are already out. We already have moles. So this one should be really, really simple. We're just taking these moles, looking at the ratio or dividing by the smallest of them, and then solving for our empirical formula from there. So go ahead, give it a shot. If you finish 2, take a look at 3. Number 3 is kind of the big one, or the harder, or the hardest of what you guys did last year. Okay, but go ahead, give it a shot. And that's it for number 2. If you've taken a peek at my presentation, that's it. It's about as easy as I could possibly make a problem for you in this section, right? We've got 0.45 moles of this, 0.45 moles of that, and 1.35 moles of oxygen. You divide everything by 0.45 and you immediately get nice whole number ratios that can't be divisible or can't be divided any further. This is your empirical formula for number 2. I hope that one was very, very simple. And again, if you're on to 3, give it a shot. But with number 3, you're starting with percentages. You may remember what to do, but let me just recap from last year. When you're given percentages in an empirical formula question, you're going to assume that you have 100 grams of this stuff, okay? So we make an assumption. We assume we have 100 grams of whatever this is. We don't know what it is yet. But if I have 100 grams of whatever this substance is, I do have 57.14% of carbon. In a 100 gram sample, that means that I have 57.14 grams of carbon, right? So really, we just assume that we have a 100 gram sample, and we take those percentages and just immediately turn them into grams, and then go through the exact same steps that we went through in the first problem. Convert your grams to moles, set up a formula with those decimal values of moles, divide by the smallest of them, and then potentially fix that formula if you don't have a nice whole number, lowest possible whole number ratio amongst them. So again, please try it. I'll shut up for a little bit here and give you a shot. That's what I have for my values of moles, okay? Again, at this point, now we set up a formula where we use these decimal values and divide all of them by the smallest quantity of moles in our formula. So I'm going to set this up. I have carbon with 4.758 moles. I have hydrogen with 6.11 moles. I have oxygen with 1.699 moles, and I have nitrogen with 0.6, oops, that's not a 6, 680 moles. I take these quantities and I divide them by the smallest, okay? When I do this, I get, for carbon, I'm getting 6.997, right? Really, really, really close to 7. Please don't overthink it. We're trying to get the whole numbers, right? And it's that close, it's 7, all right? So I have carbon 7. Hydrogen, I take 6.11 divided by 0.68. Again, I get 8.985. That's ridiculously close to 9. Please don't overthink it. We're going to call it a whole number. We're going to call it 9. For oxygen, I'm getting 2.498. Very, very close to 2.5. Again, the end goal here is to eventually get the whole numbers. I'm going to call it 2.5. And then last but not least, we have nitrogen, which 0.68 divided by 0.68, of course, is just going to be 1. And I end up with this formula. Not quite there, right? 3 of these are whole numbers. 1 of them is a decimal. We have a 0.5, which is obviously just, half. So if we take this formula and we multiply it by 2, okay, we'll get our actual empirical formula. And when I do that, you should get a final empirical formula of C14, H18, O5, and 2. Okay, this one has bigger numbers in it, right? But if you look at it, can we divide that any further? We can't. This is an empirical formula. It looks a little funky when you see the 14 and the 18. But again, there's nothing that we could divide all of those values by to make this any more reduced. This is our empirical formula. Okay. Please try number 4. We'll end it there after number 4. I have just a couple things to say after we're all done. Again, if you haven't tried it, please try it. I'll give you a 30-second head start here. This one gives us a mass ratio. Don't lose too much sleep over that. All that's saying that is that if I have 1 gram of nitrogen, I'm going to have 27.2 grams of iodine. So we are still starting at the gram spot. Convert to moles, use the moles, get to the final formula. Okay? Give it a shot. I use their molar masses off my periodic table. And I'm getting 0.0714 moles of nitrogen. And I'm getting 0.214 moles of iodine is the other one, sorry. And then again, I set up my formula, right? So now I have N subscript 0.0714, I subscript 0.214. I divide these by the smallest quantity. And when I do so, I eventually get a formula of NI3. Okay. So again, I hope this was review, or at the very least, I hope it kind of rings a bell from last year, because you did do stuff like this in regular chemistry. Again, before you leave, a couple things. AP Classroom, please sign up if you could by tomorrow. The link for that and the join code for that are on It's Learning. Sign up with your non-school email if you could. I really appreciate it, because I do want to use that for tomorrow's class. Tomorrow will be very short, maybe 15 minutes. The other thing is, if you've noticed, I do have a homework assignment in the plans. I think I had that in there yesterday even. In the back of your Unit 1 packet, okay, and hold on, let me get out of present mode so you can maybe see me a little bigger. All right, so in the back of your Unit 1 packet, I do have homework assignments. I have, it'll say HW Unit 1, Topic 1, okay, homework Unit 1, Topic 1, right? That first homework assignment is going to be due next Tuesday. The way I'd like you to submit that is by taking a picture of your like pencil handwritten work on that sheet and then uploading that to It's Learning. So I do have an assignment on It's Learning titled HW Unit 1 Topic 1. And you should be able to, like when you click on that, upload a file. Okay, so if you take a picture with your phone, you could upload it through your phone, obviously. Otherwise, Chromebooks do take pictures. If you're not quite sure how to take a picture with your Chromebook, if that's the way you'd like to do it, I can show you how to do that. If you just pop into an office hour or send me a quick email, I can explain how to take a picture with your Chromebook. But that's kind of how I'm going to do homework submission for right now. There's 3 homework topics in here. Please don't try the other ones. They're not going to make much sense. But topic 1 is due next Tuesday. All right. So I'd strongly encourage you to get a head start on that, either, today, tomorrow, over the weekend, whatever the case may be. But either way, it's going to be due by Tuesday. So if you could start taking a peek at that, and if you need help, right? If you're taking a look at it and it's like, oh, okay, this isn't going so well, find me. Please come find me. I've been chilling in my office hours all by myself, sad and lonely. So I would love to help you. You just gotta, reach out and I'd be happy to help. So that's all I have. Have a lovely day. I'll post a video of this immediately after here in the near future. So if you missed anything, I'll also post the notes of the slides and what I've worked out through on the smartboard too. So if you ever miss something during class, there should be a couple of resources every day to kind of go back and find what you need to. Okay. Thanks, guys. Have a lovely day. We'll catch you tomorrow. If anyone's still hanging around, do you have a question?